Hi, everyone. My name is Christy Kirkland. I am the Student Engagement Manager for the Partnership for Inclusive Innovation. We're very excited to have you here today. Our topic for our Smarter Together webinar today is autonomous transportation and connected roads. Before we get started, I have just a few housekeeping rules. If you're attending, if you will keep your video muted and your voice muted. And we will be recording today, and the recording of the webinar will be posted on our website. So with that, I'm going to turn it over to Alex Semiloff. He is the Senior Research Scientist with Georgia Tech Research Institute, and he will be our moderator today. So there you go, Alex.
Okay, hello everybody. I am pleased today to introduce three research teams that worked on autonomous transportation and connected road seed grant over the past 2 years, so they can present results of their research. And without further ado, let me start with the team out of civil engineering, and presenting today is primary investigator on the project, Professor Pita from School of Civil Engineering. He is also Dickerson Chair in the same school.
Okay. Thank you, Alex. I'll share my screen. I have a set of slides, so just want to see first that, let's see. Share. Oops. I'm trying to share my screen right now. I'm not sure whether you're able to see my presentation.
Not yet.
Oh, not yet. Oops. Okay, so desktop 2. Okay.
While presentation is being pulled up, I also wanted to ask if anybody during presentations have any questions, please put them in the chat. After presentations are concluded, we'll be able to answer some questions and have some discussions.
So how about now? Are you able to see the presentation? Yeah.
No.
Oh, not yet. I'm sorry. Oh, boy. Let's see if this works. Stop 2. Share. Okay. So I think there are some issues maybe with my share preferences. Okay, there we go. I think this was related to something that I'm going to anyway quit and come back, I guess, because if I do share, it says that I have to quit. I apologize for that. If somebody else wants to start, that's fine. So.
Okay, yeah, let's start with, I don't see Anton, but Zuni, if you introduce yourself and you can share your screen and start to present.
Yeah. Hi, everyone. I'm Xianyu. I'm a fourth-year PhD in operations research from the Department of Industrial and System Engineering. So today, my advisor, Professor Anton Klavets, will be presenting on our research for pickup and drop-off facility design for autonomous vehicles. Yeah. Should we wait for Professor Anton to start the presentation?
If he's not here, I would probably start, and if he joins, he can maybe talk at the end of it.
Okay. So do you want me to start the presentation right now, probably? If that's
yes.
better place? Okay.
Yes.
Okay, can everyone see?
Anton has just joined. So,
okay, great.
Anton, are you online? Do you want to say a few words, or do you want to start the presentation?
I'm sorry, I just struggled to get the mic to come on.
Yeah, we can hear you. So if you can, please briefly introduce yourself, and then we can start the presentation portion.
Okay, excellent. I'm Anton Kluivert. I'm a faculty member in Industrial and Systems Engineering at Georgia Tech. And Shenyu and I and a few of our other students work on transportation problems, especially problems related to autonomous vehicles. And I'm very happy about the work that Shenyu is going to present today. Shenyu?
Yeah, can you share your screen?
Yep. Okay, thank you, Professor Anton, for the introduction. So can anyone see my screen right now?
Yes.
Okay, great. So today I'll be sharing on the project that Professor Anton and I worked on basically on the problem of pickup and drop-off facility design for autonomous ground transportation. So problem, I'll just give a brief overview of how our problem is defined and how our scope is identified as well. So the problem description here shows that our work aims to provide a computationally inexpensive and empirically verified method for design of efficient pickup and drop-off facilities for on-demand transportations. And recently, we can see the need for such carefully designed pickup and drop-off facility, especially for autonomous vehicles, as autonomous vehicles will be able to park themselves. So human drivers do not necessarily need to drive the vehicle to and from certain parking lots, but instead this vehicle themselves can pick up and drop off passengers at the desired location. That is the original destination of the trip of the human travelers. And in our study, we specifically focus on two points. The first one is that we want to optimize the trade-off between certain performance criteria and the space utilization. And then the second one is we would like to model the conflicting movements of vehicles and as well as those between the human pedestrians and the vehicles. Here are certain facility layouts that we're examining, and our goal is to look out for the best facility layouts among several types I'm going to introduce right now. So the first one is a very common one. It's called a single lane configuration, such that there is a single driving lane and vehicles can park on the driving lane and pick up and drop out the passengers on this single driving lane. And similarly, we have a multiple lane configuration that's just parallel single lane configurations. And then we can treat the system as independent lanes that are each operating on their own. And we can see this example quite frequently at places like airports. The next configuration is called a single-sided zero-degree configuration. By single-sided, we mean that there's a boarding area with boarding spots on only one side of the driving lane. And by zero-degree, we mean that each boarding spot in the boarding area is parallel to the curb. That is, the angle between the boarding area and the curb is 0°. And similarly, we have a double-sided analogy for single-sided design such that each driving lane is neighbored by two boarding areas on its both sides. Similarly, we have a single-sided 90-degree configuration. It differs from the 0° configuration in that each boarding spot is orthogonal to the curb space, such that the angle between them is 90°. And more often than not, in practice, we can see angled configurations in the sense that the angle between the parking lots as well and the curbside could vary from angles like 45°, 60°, or 75° as well. And we would just like to highlight that our model can accommodate for all these different combinations. So without further ado, I'll just jump into the numerical results and share some insights that we observed from our simulation results. So next, I'm going to present basically 6 types of configurations. So as we have seen just now, we have single-sided versus double-sided configurations. We also have 0° configuration versus 90° configurations. In addition, we consider 0° configurations with long spots, such that each boarding spot is long enough for vehicles to enter and exit, both by going forward. And another alternative to the 0-degree configuration is when we have short spots, such that vehicles have to back into the boarding spots, like when they enter a boarding spot. And for 90-degree configuration, for safety considerations, we assume that vehicles always enter by going backward and exit by going forward. Here are some results that we would like to highlight when we assume that the mean service time, which is the time taken for loading and unloading passengers as well as luggages, to be 60 seconds. This is a plot of how the throughput capacity of each kind of configuration varies as the total number of boarding spots considered in the facility varies. So here the main insights are the following. First, throughput capacity increases as the number of spots increases, but at a decreasing rate for each configuration. This is what we always observe in real world as the decreasing marginal return. And also, in terms of which configuration is the better choices for this specific mean service time at 60 seconds, we also observed that single and double-sided 0-degree configurations with long spots have much larger throughput capacities in general. That is this yellow curve and the orange curve on top of the others. And similarly, we could also analyze the throughput capacity of the facility versus the area that it occupies. In this plot, we can say that instead of having the number of spots on the x-axis, we have now plotted the area that is occupied for different configurations. And it's worth noting that because different configurations illustrate different lengths and widths for each boarding spot. So with the same number of boarding spots, different configurations might occupy different area. We have two insights highlighted here. The first one is double-sided 0-degree configuration with long spots utilizes the space most efficiently for medium to large size facilities. That is from the orange curve on top of the graph. And we also observe that single-sided 0-degree configurations and single-link configurations can be desirable choices for larger facilities depending on the shape and size of the available spaces. So that is this filters around here. By the shape and size of available space, we also consider in practice what is the available facility size that is different based on the case-by-case scenario. And for example, if we consider a single link configuration, then that will most likely require a rather linear and long-spanning space. And so far, we have looked at a service time at 60 seconds, which is around 1 minute for each vehicle's pickup or drop-off activity. And that could be relatively short or on the shorter range of the service time that could appear in real life. So now we consider the other extreme, which is most likely the upper bound for mean service times, that is around 300 seconds or 5 minutes. So we can see that the curve now actually exhibits a really different pattern than before. And with longer service times, we observe that double-sided 90-degree configurations becomes a configuration that utilizes the space most efficiently. Also, in general, we can observe that single-sided configurations have less throughput than their double-sided counterparts, partially because when we have much longer service times, the efficient utilization of space is more important than the savings or in time for more spacious configurations which facilitate faster enter and exit maneuvers of vehicles. And in this case, we also observed that single link configuration becomes the most inefficient choices because the blocking among different vehicles is maximal in this case. Another main part of our research is that we also look at different kind of access controls at the entrance of the facility, such that under this specific access control, we aim to provide the optimal system throughput or near optimal system throughput. So several alternatives we considered are full access control, partial access control, and optimal access control. So full access control is the most restricted version of access control, such that all vehicles are coordinated and no traveling vehicle is ever blocked on this route lane. And it's a scenario that resembles the connected and autonomous vehicles coordinated by infrastructure, such that all the vehicles in the system has full information on the other vehicles in the system. On the partial access control alternative, the entrance of the replacement vehicle is partially coordinated, such that vehicles may slow down or come to a complete stop if they're delayed or blocked by other leading vehicles ahead of them. And for optimal access control, we derive this policy by solving a Markov decision process formulation. And basically, the policy that is returned by this formulation will decide the entrance of replacement vehicles, and as well as the assignment of boarding spots to each individual vehicle. In this case, vehicles may slow down or stop, as long as the MDP, in the long run, it is optimal to allow the entrance or access of the vehicle. So for now, we may assume that optimal access control is the one that is the best that this facility design could achieve. And next, we show a comparison of how full and partial access control performs as compared to the optimal access control. In these two plots here, so for example, on the left, we have for single-sided configurations. Here we plotted out the percentage deviation of the performance of full or partial access control for each specific number of boarding spots considered as compared to the optimal. So as we can see, the deviation increases as number of spots considered in the facility increases. And also for configurations like single-sided 0-degree configuration with short spots or single-sided 90-degree configurations, such that each boarding spot occupies smaller space, as well as, and they are also considered as the more compact configurations. The deviation increases very fast, especially for partial access control. And we may have similar observation for double-sided configuration here. So in general, throughput capacity under full access control could be near optimal for nearly all the configurations, while partial access control can be suboptimal, especially for these compact configurations. So we hope that this would actually help people who design and operate such facility to decide what might be a better access control policy to increase the throughput of the facility. And especially in the case that MDP solution, which is optimal access control, is very hard to solve. So simple policies like full and partial access control could be very helpful in practice. And through our study, we also found out very interesting suboptimal dynamics under partial access control. This is an example from the single-sided 0-degree configuration with short spots, such that the blocking is actually is relatively more significant among vehicles. And by running the simulation, we found out the system runs into a state such that the leading replacement vehicle in each platoon are assigned to boarding spots that are closer to the facility entrance. And while they are having their intermaneuver into the assigned boarding spots, they're actually blocking the entire platoon that's behind them. And by that, there is actually a very large degree of blocking among vehicles that is happening. And so this is what we consider a very suboptimal dynamic of the system. And it's worth noting that by default, the boarding spot assignment or choice rule is to assign the spot that is closest to the facility exit to a vehicle. So which is by default, the desirable behavior of the system is very different from what it exhibits after a long time or in steady state.
Okay, Juni, 2 minutes.
Okay, thank you. And here we show how this suboptimal dynamics evolves over time once it has reached steady state. So as we can see, this is from a time period of around 200 time interval, and it goes on to almost 1,400 time interval. And we can see here, the first column has a very similar pattern to the fourth column. And so it's the second column and the fifth column, as well as the third column and the sixth column. So it suggests that once the system runs into this suboptimal dynamics, it will just keep on looping and looping again, and it will never get out of this suboptimal state. And we also try to manually reassign the boarding spots in one state of this loop. And the result is the system returns to this bad behavior within several hours of simulation time. So in a sense that this suboptimal dynamics is very robust when there is more perturbations to the system. Yeah. And next, I would also like to quickly go over some other considerations we had in our study. The first one is the comparison of different input distributions. So here we show straight plots here, and the main takeaway from this plot here is that the mean service time, mean service time is kept the same for all input distributions. The variance of the movement times has a much larger effect on the throughput capacity as compared to the variance of service times. And just to illustrate that, in this yellow curve, we have exponential service time and deterministic movements. And we can say that by having deterministic movement, the system actually achieves a much higher throughput capacity. So this also in some ways suggests that if we have a system that is fully operated with autonomous connected and autonomous vehicle with synchronized movements, that will increase the throughput of the facility in a significant way. And last, we also consider a double parking, which is a bad behavior, and it somehow also creates the safety concerns. And just to quickly go over these results, we found out that even though double parking configurations occupy the same space as double-sided 0-degree configurations, the throughput is much less than the double-sided 0-degree configurations. Okay, yeah, and so this basically wrap up our presentation today, and we hope that these insights that derive from our numerical simulation could be shared and discussed among people like our attendees today. And also we have, this is our 2 papers. One of them is in preparation that we are presenting these results, as well as the method we use to derive the numerical results. Okay, with that, I'll end my presentation here, and yeah, thank you very much.
Thank you. Yeah, we'll leave questions to the end of our webinar. So while Dr. Peter is connecting, let me just mention that all of those projects were done in close cooperation with City of Peachtree Corners and Curiosity Lab at Peachtree Corners. That's why, I mean, throughout the presentations, you will see some references to that. I don't know if representatives from Peachtree Corners were able to connect, but we all really appreciate their support and their willingness to work with us and their flexibility. They've been great throughout that experience. Okay, Srini?
Can you see my screen again?
We can, but it's like really zoomed in. Oh,
it's zoomed in?
Yeah, we see basically Georgia Tech logo. Yeah, okay. Now it's in presentation is in design mode.
Okay, so just present in the design mode. Okay, got it. So, is that better? So
no, now we see your notes as well.
Oh boy.
Or outline, actually. We see outline of the presentation.
Okay, what I'll do is I'll share my just a screen. That will be the easiest way to address this, I guess. Otherwise, I don't know how to get past this. So, alrighty. So let me go here and see if I can do it again. How about now?
Now it's okay. We still see it in design mode, but that's fine. It's visible.
It's feasible, okay. I'll just try to put it in presentation mode once. If it doesn't, I'll come back to the design mode. Is that better?
Well, we see presenter's screen now.
Okay, so well, let's go with this then.
Yeah, this is fine. This works.
Okay, wonderful. Sorry about the situation I've been having. I'm still trying to figure out what's the challenges here when I'm changing. Okay, so let me go back to my, okay. So this particular presentation is based on work, as Alex mentioned, for the city of Peachtree Corners in Curiosity Lab. And the intent of this presentation was to see what are the effects of autonomous vehicle technologies, both in terms of how they affect infrastructure and also driver preferences related to how those infrastructure interactions in the presence of autonomous vehicles would work. So this was in the context of a presentation related to first, when we look at emergent technologies, whether they're autonomous vehicles, autonomous automation, connectivity, or electrification, all of these lead to challenges that are particularly, in some ways, transformative, but especially the autonomous technologies are particularly disruptive as well, because they involve handing over control to the vehicle or to the autonomous system in a vehicle. So when we look at most of the focus, especially in the media, it relates to how some of these autonomous technologies enhance the driving experience, but also some of the pitfalls they illustrate. So a lot of the focus has been related to the technology itself. But in the real world, the reason why these technologies are not yet widespread is because in society, there are interactions between these vehicular technologies with the human, the driver, and the surrounding people in the traffic environment, as well as with the infrastructure as well. That is, whether the current infrastructure is adequate, are the changes that need to be made. So it's these interactions that we illustrate here through these arrows that become particularly important to understand. And in terms of background, when you look at autonomous vehicles, a lot of the work that's been going on related to understanding how they can be introduced into society and transportation systems, they're either in terms of controlled test beds, or more living lab type test beds. For example, Curiosity Lab is one of them. I'll be talking about that. And then pilot studies, for example, how Waymo has introduced cabs in the vicinity of the Phoenix area. And they entail also partly infrastructure modifications. And some of these modifications can be in terms of having dedicated autonomous vehicle lanes where only autonomous vehicles can travel, having barriers that separate the lanes for autonomous vehicles from the regular vehicles that are driven by humans, having pick up and drop off lanes where we have vehicles coming, dropping off and moving elsewhere, which is particularly important in dense urban areas. And also there are roadway markings. And all of these you will note if you look at the Curiosity Lab current design there, which is a 1.5 mile stretch of roadway, which has a dedicated AV lane. So in both directions, there's a dedicated AV lane. There's also at the time of our work, there was a AV shuttle that used to operate in this lane. And in addition to this, you'll see that there are plastic post barriers out here that separate that from the regular lane where human-driven vehicles are. And also you see road markings out there. And in terms of what the current design entails, if you look at it on the left side, you'll see that there are 4 lanes, and that's what you see here on the right side if you look at the figure as well. And the current one has 1 travel lane in each direction for non-autonomous vehicles, and then there are dedicated lanes for autonomous vehicles in each direction, so 1 lane each. The key point to note here, which you possibly will not note, is that the regular travel lane for human-driven vehicles is 10 feet 6 inches, and the other one for autonomous vehicles is only 9 feet. And part of that justification, it is the expectation is that autonomous vehicles are much more reliable in terms of maintaining their lane position, unlike humans who tend to drift, and there's heterogeneity in that. So so autonomous vehicles would require lesser amount of space, but this has implications too. And then there are the barriers that I mentioned that separate the autonomous vehicle lane from the regular lanes. Then the next one is an alternative in which we have all lanes, 2 lanes in each direction, which are for autonomous vehicles and human-driven vehicles. And the idea is that we'll get to this point when we have autonomous vehicle market penetration, which is at a substantial level, or they become more commonplace. And again, this was based on discussions with Curiosity Lab and Peachtree Corners in terms of what other infrastructure designs they wanted to test. So they have 2 lanes in each direction, but these lanes are unequal, as I mentioned, because one lane is still the inward lane is still 10 feet 6 inches. The one which is close to the curb is 9 feet, and so they share the road between the autonomous vehicles and the human-driven vehicles, and there are no plastic post barriers, because at this point the idea is that people are comfortable driving on with autonomous vehicles. And then there's a second alternative to this, where if you look at this diagram here to the right, you'll note that in one direction there's this single lane where you have mixed traffic flow of autonomous and human-driven vehicles, and next to that, which is barrier separated, we have lanes in opposite 2 directions where bicycles or scooters can go. So at the corner there, which was previously the autonomous vehicle lane, that's been translated into a 2-way bicycle scooter type lane. And the other direction, again, it's similar to what we had in the previous alternative, which is alternative 1, which is where any autonomous or human-driven vehicle can go. There is no separation involved. And based on this, the objectives we aim to study, there are twofold. One, the interactions between the human driver, and the infrastructure. And this is in the current design and in alternative 2, because there is also the plastic post barrier separating the lanes there. Whereas when we look at to capture the effects of autonomous vehicles on the human driving itself, the idea is is that what are the interactions that happen when autonomous vehicles are there in a mixed traffic flow stream. So we conducted driving simulator experiments, and these experiments were based on the driving simulator lab, which is called the Autonomous and Connected Transportation Lab at Georgia Tech, from which we had kinematic data, which is the driving data. So where participants would drive, we could get the speed, acceleration, braking information, but also their physiological information. For example, you get information using EEG on their brain signals, ECG, their heart signals, then the non-intrusive way of tracking where their eye position is. And that's important to understand where people are focusing and whether there is too much load. And then also the driving behavior in terms of the position of their head, hand, legs, and so on. And what I'll show next is, there you go, oops, is how that showed up in the simulator. And so what you see here is the current design in the simulator, where the participant would see the dedicated AV lanes, which are separated from the regular human-driven vehicle lanes using plastic post barriers. So that's the current design that's out there. And from there, we shift to the next one, which is where both autonomous vehicles and human-driven vehicles can go on either lane. As I mentioned, we have to recollect that the lanes in each direction are of uneven width, and there are consequences to that as well. And then if you go a little further, we have the alternative 2, which is we have mixed flow of and dedicated bike lane in one direction. So as you can see here, there's one lane for autonomous and human-driven vehicles, then there is one for bicycles in either direction. And on the other side, you have just like 2 regular lanes available for both human-driven vehicles and autonomous vehicles. And with that, I will go to the findings. So I'm moving to the next slide now. some reason it's stuck. There you go. We have for alternative one, what we note is that when we have the two lanes that are freely available for vehicles, so vehicles can overtake other vehicles. So in general, the average speed tends to be higher. But on the other hand, because we have one lane which is narrower than the other, the ability to shift across lanes and overtake and so on leads to less stable trajectory because people are in some ways confused by lanes which are short, have smaller width as opposed to a lane which is more wider. So that tends to throw off people and tends to cause confusion. So that's something to keep in mind. Even though originally when we look at it, it's because of the hypothesis that autonomous vehicles require a lesser amount of space. The third one is related to human response. And this is mostly an artifice of our experiment in the sense that even though the characteristics of autonomous and human-driven vehicles were different in the experiment, there were no overt or outward physical signals that would allow the participants to differentiate between autonomous vehicles and human-driven vehicles. And so they treated it as identical. And if you look at alternative two, where we had the mixed flow and dedicated bike lanes, again, two aspects to keep in mind. When there's a lane next to the dedicated bike lane, so that's the case where only there's one lane available for mixed traffic flow. So that caused people to feel less comfortable because there's just that one lane. And then it also raises safety concerns because they cannot cross the yellow line if vehicles are coming in the other direction. So that is something that was also identified. But from an aspirational standpoint, people felt that sustainable transportation designs would be particularly useful. So they actually liked the notion that we create space for bicycles or e-scooters. And this has consequences, or it has implications, because these days we have micro-mobility services or modes that are coming into play. And there is a notion there that these are legitimate travel modes that can be particularly helpful in society. And the last slide here is related to the other findings. And primarily, what we noticed is participants who had greater amenability to using autonomous vehicles also felt more optimistic about driving besides them in a traffic stream. So versus, I guess, those who are more hesitant. The last point that I want to make is that there are consequences in terms of infrastructure design. First, the brain and heart activity were more prominent within the intersections. And this was not surprising because intersections are locations of conflict of right-of-ways. So naturally, people are more alert. The same thing happens, however, when we have a plastic post barrier and a median. So in many ways, people are boxed into one lane. And at that point, what happens is there are people who want to watch both of these directions. And so there tends to be more activity which gets triggered in terms of their conscious effort. And that's why that increases as well. The third one is, in the case where we had alternative one, when there are two lanes, if there was a median between the two directions, the opposite directions, then people had less focus in terms of eye movements because they were assured that the median was protecting them from going to the other lane, or they were not worried about traffic coming from the other direction. So this is the final point that I wanted to make. And so this concludes the presentation that I wanted to make today. Thank you.
Okay. Thank you, Srini. And final presentation for today is presented by Brian Lee. He is representing a team out of Georgia Tech Research Institute, and he's going to talk about secure and connected vehicles.
Alex, can you see the slides?
Yeah, now I can see it in, if you can minimize that panel on the left. Now I see, you need to switch to, now I see presenter's view.
Okay, 1 second. How's that?
Yeah, now it's better. It's a little, I guess, a little too zoomed in, but I think that's okay.
It's okay. Okay, so I'll continue like this. Okay. Hi, my name is Brian Lee. I'm a research engineer here at GTRI. I'm going to be talking about the Secure and Connected Vehicles project I was able to be a part of. So I guess just quick background. So what our project entails is utilizing these DSRC or CV2X radios. Essentially, these are short-range wireless communication devices. So the standards are they want to essentially integrate these radios into vehicles, so vehicles have a separate channel for communication. So for our project, we procured 2 DSRC radios as well as 2 CV2X radios. Again, these are competitors, but most recently CV2X is the front runner right now. That's why we've actually purchased an extra pair of radios. Where our project kind of stems from is that when we go through the standards, in this case, the 1609.2 standards that outline the security services, they outline in terms of cybersecurity or cryptography, suggestions or guidelines. These aren't always restrictions. So we noticed that some of these vendors had missing pieces that we thought we could implement. So basically our goals here are implement an encryption decryption module on top of a vendor's software stack, test the radio's performance metrics, and then with a little extra time at the end, what we decided that we kind of wanted to check out was, hey, can we fuse some of the information from these CV2X messages, such as GPS information, with onboard vehicle camera data? So essentially, a camera has a certain field of view. Can we increase that field of view with these car messages? So I guess, why do these vendors not really encrypt? Why is this component missing, right? So for these radios, the primary type of message that they use are broadcast type of message. Here they call them wave short message protocol. And they use these broadcast messages essentially for safety critical messages, right? So if a car is braking all of a sudden, it wants to send a quick message back to the cars around it. Hey, I'm braking really hard. You guys should watch out, right? So for collision warning systems, in this case, these broadcast messages are generally untargeted and they're not really deemed as sensitive. So there's not really a requirement for encryption. But in our case, we thought there were a good amount of use cases where encryption would come in handy. Let's say there's an army platoon of vehicles trying to travel around. They want to communicate with each other, but they don't want other people to be able to listen in or intercept those messages. So essentially, the procedure itself wasn't too difficult. What we do is we create a C module that handles the encryption and decryption. So in this case, we'll have some sort of payload. In our case, it was a message. We'll encrypt that payload. And after that, we'll send it through the rest of the vendor's software stack. So we'll encode it, we'll encapsulate it, we'll sign it for integrity, and then we'll send the message out. So essentially, we just kind of figure out a way to, hey, incorporate this encryption piece to the stack. So in terms of initial results that we received from the radios, in terms of performance, from a short range clear line of sight, so we were about 10 meters away. Without encryption, we're getting a latency of about 5 milliseconds, 5.2 milliseconds. When we add that encryption layer, it adds a little less than a millisecond to it. At a longer range with more obstructed view, so we couldn't see the other car clearly, about 200 meters away. Here, the mean latency was about 7 seconds. And again, we add about a 1.2 milliseconds with encryption. So in terms of other research papers, as well as the performance metrics that the vendors provide, they're advertising about 10 milliseconds is what we should be expecting. So both cases meet that 10 milliseconds threshold. And again, these are very small packets. So encryption isn't as delayed or cause significant delay. We did make some generalizations. So in our case, every user has access to the symmetric key. It's basically saying that you don't have to create a handshake or connection with another user before exchanging encrypted messages. This may not be realistic. I guess other approaches that you may want to try this is maybe using a public key infrastructure, right? So in this case, when a car drives next to another car, when it's in its radius, they'll say, hey, I want to send messages with you. I'll create a public, we'll exchange information and agree upon a symmetric key. And from there, we can encrypt messages. Again, this is just too slow. it wouldn't make sense if random cars just passing by trying to create messages, and that at the same time, you would also need more hardware to handle all those connections. Something more reasonable would be having some sort of central entity that would be responsible for the symmetric key, and then vehicles would essentially register with that central authority. And if they pass the registration, they'll get a copy of that key. So essentially anybody in that single group would have that symmetric key where they could, send out messages and read others' messages. In my opinion, that's probably the way to go for this use case. So the second part we decided to do was we had this data fusion idea, was really just syncing together the radio messages with the camera data. So in our case, we used the CV2X radios, and then we used a dash cam video. So our processed output from here is on the right. You'll see what the dash cam is looking at. We applied on top of that a tracking algorithm for vehicles. So you'll see here, I'll put a box around if it thinks it's a vehicle. On the left, we have a Google Maps overlay with red dots and blue dots. Here, the red dot corresponds to the vehicle that has that camera feed. And then the blue dot is the other vehicle that also has a radio that's transmitting messages. On the right side, you'll see just from the BSM messages, we can calculate how fast that vehicle is going, the heading, the direction it's facing, as well as how far we are apart from the other vehicle. So there's a lot of metadata or additional data that really just expands our view of our surroundings besides just a camera view. I don't know if we have a lot of time, so I'll just skip the video. But essentially what we got here was when we got about a max range of about 760 meters here. So, 760 meters away, there's no way a camera or a LiDAR is going to be able to detect that. So it definitely expands our field of view. But a caveat is that the CV2X radios that we received were experimental radios, as in they're more for development and not for performance. So what we did see was, even though the vehicle is right in front of us, clear line of sight, we weren't receiving packets, or we weren't able to listen to packets. So we're definitely transmitting, but the receiver module was having a little bit of trouble there. I guess some concluding thoughts after going through that research project. I would say the CV2X standards are still developing. So I think it's a great area for research where, the value can be added here. Some things that actually kind of worries me is actually with these new radios, if we do implement these on vehicles, we're really just introducing a new attack vector. So I think automotive cybersecurity really needs to be on point here, right? Not just protecting the vehicle itself, but connecting the communication networks that it's part of. Then this project really just gave me more of an appreciation for that, because with vehicles, it's more about people's lives that are at stake instead of servers where, you might lose your users or a bunch of money. But I kind of wanted to end it with, let's go automotive cybersecurity.
Okay, thank you, Brian.
Thank you.
So with that, we conclude portion of presentations, and now we'll move into discussions. So like I said, if anybody has any questions, please put it in the chat. So far, I see only one, and it's from Anton to Brian. Brian, you mentioned that CV2X is a front runner compared to DSRC. Can you elaborate on that?
Yeah.
Isn't DSRC being phased out?
Right. So I would say about 2 years ago, DSRC was the front runner because of their performance, right? So they did have lower latency because CV2X were using 4G chips, right? With the upcoming of 5G chips, CV2X was able to get that as good as performance as DSRC. So essentially what they're saying is, hey, it's easier for us to upgrade mobile chips than actually having to, dedicate all of our resources to upgrade DSRC software or hardware. So that's kind of the main reason why it's shifting towards CV2X. It's because 5G was able to get the performance that DSRC was able to get.
Okay. Okay, thank you. I don't see any more questions in the chat, so I'll ask, I ask my own question. So all of those projects that you guys worked on, in one way or the other, are touching infrastructure. And there are, I guess, two groups of thoughts, and I can probably argue for both of those. One basically saying we should not be changing infrastructure and we should be adapting autonomous vehicles to infrastructures that already exist. And then second group of thought saying, well, we probably should take, we probably should change infrastructure and take advantage of all the features and efficiencies that we can get with autonomous vehicles. So what are your thoughts about, should we design vehicles to fit what we already have, or should we think about changing infrastructure to accommodate those vehicles?
Alex, can I take a response for that?
Yes, yes, sure.
So,
it's a question to everybody. Yeah.
Sure. So, you know, I look at this as something where we are today and what is the ultimate goal if you want to look for sometime far in the future, where we are hoping that the whole traffic stream consists of, say, autonomous vehicles. I'm just saying that if where we are today to where we're going. So what is important is that there is a transition period that's going to be there, and that we don't know how long that's going to be, but it's going to be there if we want society to smoothly and bring in these new technologies, autonomous vehicles, into society. Right now, we have mostly human-driven vehicles. We have human-driven vehicles. We hardly have any autonomous vehicles in the traffic stream. So given that, the question is, if you look at it from the perspective of the human, typically there is that incremental notion of, okay, I feel comfortable with what I have, and this is something that society has been used to for such a long time. Then we introduce technologies that are radically different. They can lead to a lot of disruption potentially. And so there is an argument for trying to do that incrementally. And this is something I guess would also fit well with vehicle manufacturers as well as with where things are. Because when you talk about infrastructure investment, I'm not talking about just in terms of the roads, but even in terms of, say, the connected infrastructure that can be used to leverage autonomous vehicles and so on. But over a period of time, there seems to be value in terms of infrastructure itself adapting to the benefits, of autonomous technologies. Otherwise, when you look at autonomous technologies, there are aspects there that they provide benefits related to. First, just to illustrate related to the infrastructure, they don't necessarily weave on a lane, so you can have smaller lane widths. But given that, if I talk to my colleagues, say, who do pavement-related work, they'll say that if vehicles are so precise, then they form all these depressions on the road, and that can be a consequence of this. So there are trade-offs which are emergent that we need to understand well. So that's the first point. The second thing is, with autonomous vehicles, the idea is that at some point we can have the headways sufficiently low enough that the capacity of the roads without widening the existing roads could potentially increase. So there are benefits of trying to adapt our infrastructure over the long term to the benefits that supposedly are offered by autonomous vehicle technologies.
Okay, thank you, Srini. Anton, Zuni.
Yes. Thank you, Alex. Yes, I would like to add a few things to that. So there are kind of two very different approaches to designing autonomous vehicles. So the one approach tries to design vehicles that can operate like human-driven vehicles independent of any interaction with infrastructure. So it doesn't need any communication with infrastructure or communication with other vehicles. And that's the approach that's followed by most of the developers of autonomous vehicles today. Companies like Waymo, ATG, Cruise, etc. They are designing autonomous vehicles without relying on infrastructure support. And the other approach is to use the infrastructure to control the flow of the vehicle. So the vehicles, so infrastructure becomes an essential part of the whole system. there are arguments in favor of both sides. So I just briefly want to summarize what those arguments are. Arguments in favor of the autonomous, independent of infrastructure approach is that to put infrastructure in place requires a lot of coordination. As Brian indicated, there are different standards, different types of technology that are competing with each other. And people, they are competing, and people don't agree on which is the technology that should be used. And the developers of autonomous vehicles, again, like Waymo, etc., they don't want to wait for people to agree on the standards and the technology that should be used before they develop their vehicles. So they have followed the approach that they're not going to wait. They're going to develop their vehicles to use, to work, whatever the infrastructure that will maybe added later. But there are a lot of disadvantages to that approach. Some disadvantages are every vehicle has to carry its own technology, its own LiDAR and cameras. And another disadvantage is the ability of the LiDAR and cameras mounted on the vehicle to locate the vehicle, to see what is going on in the entire traffic flow is quite limited. If you put cameras or if you put devices on light poles high up, it has a much better view of what's going on in traffic flow. And when I worked at Uber for a year, and when I worked there, I saw the same thing happening. I saw an autonomous vehicle that got stuck behind a truck, and it didn't know whether it should pass the truck or whether it should stay behind the truck in the lane because it couldn't see what was going on in front of the truck. Whereas if you had infrastructure with a better view, you would know what is going on in the traffic flow in front of the truck. And then I think the most important shortcoming, this is from my point of view, most important shortcoming of this independent autonomous approach is that it does nothing to improve traffic flow. So Srini mentioned that maybe the headway can be reduced, but I think reducing headway contributes relatively little to improving the capacity of traffic flow. And in our street networks, most of the delays take place at intersections. And to improve traffic flow through intersections requires some coordination. It requires coordination of the flow of the vehicles through these intersections. And that can be done with independent autonomous vehicles. You need some infrastructure and coordination to do that. So again, advantages of infrastructure, it can, I think, do a much better job of improving traffic flow. I think it's overall is more economical. It's more economical to have to pay for the infrastructure than to put all these devices on every individual vehicle.
Okay, thank you, Anton. And Brian, we have 1 minute left. So if you have quick remarks.
Well, I think I would just say I think what's going to be kind of an afterthought is just cybersecurity. I think with all these infrastructure and vehicles, and we start just pumping all this, new devices out, new smart cities out on the side and we're in parallel, I think cybersecurity needs to be mentioned. I think that's kind of my last thoughts I wanted to put out there.
Okay, thank you. I wish we had another hour to continue to talk about this topic. Obviously, everybody is very excited about this area, but we are up an hour. So, Christy, do you want to say final words?
Thank you so much, Alex, and thank you to all of our panelists today for this great discussion. We appreciate everyone joining in with us today and hope that you can join us for our final Smarter Together webinar on Thursday, December 2nd, and the topic will be inclusive entrepreneurial environments. Hope everyone has a great day. Thank you so much.
Okay, thank you. Thank you all.